Hi, Hire. This week we are moving on to a new subtopic, which is in Unit 3, Chemistry and Society, and it's called Equilibria. So, Lesson 1 is Equilibria and Changing Concentration. Our learning intention is to gain an understanding of what is meant by dynamic equilibrium and investigate how this is affected by certain factors. Success criteria is to define dynamic equilibrium and identify factors which can affect the equilibrium and explain why this happens in detail. So, first of all, what do we mean by equilibrium? When a system, that just means a reaction, is at equilibrium, this means the rate of the forward reaction is equal to the rate of the reverse reaction. And that is kind of your definition for equilibrium, what it means. If we look at this on a graph, then as the forward rate is happening and decreasing, the reverse rate is increasing, and at a point, these rates will become equal. And that's represented by the straight line here. So as time goes on, reversible reactions will start off quickly in the forward and reverse directions, and then after some time they will reach an equilibrium, which just means the rates even out and become equal. This, however, does not mean that the quantities of reactants and products are equal. You might end up with a mixture of 20% product and 80% reactant. And this again is shown on this graph here. So as the reactants decrease in, well, we would say at concentration. I know this graph says amount, but we would say concentration. So as the concentration of reactants decreases because they're turning into products, we end up with this concentration here. Let's say that's 10 on the graph. Our products are increasing in concentration as they are being made by the reactants, and they level out up here on the graph. Let's say that's 30. So as you can see, even though they are at equilibrium, there is no change in concentration. There is not equal concentrations of reactants and products. That's very, very important. The rates are equal, but the concentrations aren't necessarily equal. What I'd like you to do is I would like you to go to watch this video. It's a really good video which shows you equilibrium right in front of you. If we had been in class right now, I would have done this demonstration just to show you exactly what it looks like. So what I want you to do is have a wee watch of this video. I will link it in your Google Classroom post. And I want you to, on that page of your notes, write what you learn from the demonstration in your own words. I think the video is about 6 minutes long, but it's really, really good for showing how equilibrium actually works in real life, because talking about it is very abstract and it's difficult to understand unless you see it right in front of you. So let's have a little question then. This is a typical multiple choice question. Chemical reactions are in a state of dynamic equilibrium only when A, the reaction involves no enthalpy change, B, the concentrations of reactants and products are equal, C, the activation energies of the forward and backward reactions are equal, and D, the rate of the forward reaction equals that of the backward reaction. Well, we just learned that the concentrations of reactants and products are not equal, so it can't be B. A, the reaction involves no enthalpy change. Well, we know that all reactions involve an enthalpy change, so it's not A either. The activation energies of the forward and backward reactions are equal. We haven't covered this yet, but in time you'll find that that is also untrue. So it should be D, which is what we learned a few minutes ago. The rate of the forward reaction equals that of the backward reaction. Lots of people will get this wrong because they get the rate and the concentration mixed up. They will look at this in a panic and find the word equal and immediately pick B. So you need to be really, really careful in these questions and make sure you look for the rate of the forward reaction equal to the backward reaction and not the concentration. So we can actually alter this position of equilibrium. And there are 3 different factors which we are going to look at which can affect this position. These are concentration, pressure, and temperature. So once the reaction has reached this equilibrium point, where the forward reaction rate equals the reverse reaction rate, that equilibrium will stay there forever, just going backwards and forwards and backwards and forwards, unless you do something to it. And what we can do is we can alter the position of that equilibrium to suit us. So if we want more product to be produced, we can influence the position of equilibrium to shift more to the product side. If we want more reactants to be produced, we can do the same. We can change one of these factors and make the equilibrium lie closer to the reactants side. In this lesson today, we are only going to look at concentration, and we will look at pressure and temperature in lesson 2. Again, had we been in class right now, we would be doing this experiment for real in front of you. But you do have an experimental write-up in your booklets that I'd like you to complete as we talk through what happens in this experiment. Hopefully, if we end up back in classrooms, we can actually do this as well. So our aim is to investigate the effect changing concentration has on the position of equilibrium. And for our method, we are going to start with 4 test tubes, which all have the same solution in them. I'll tell you what that is in a wee second. Even though the diagram shows it in a kind of watercolour, these are all quite pale yellow. Number 1 is going to be our control. So we're just going to keep that the pale yellow colour. Number 2, we're going to add some iron chloride. Number 3, we're going to add some potassium thiocyanate. And number 4, we're going to add some ammonium chloride. And that ammonium chloride is going to remove iron 3 plus ions from the mixture. So to understand how these factors are going to affect the equilibrium position, what we need to do is we need to look at the equation. And we're given this equation here. This is what we're interested in. And this tells us that the iron 3 plus ions are a yellow colour. If you remember back to Nat 5, you know that different ions have different colours in solution. This is telling us that Fe3 plus or iron 3 ions are yellow. The thiocyanate ion, which is this ion right here, is colourless. So this is the reactants. These are reacting together to produce this iron thiocyanate, which is a red colour. So we have the yellow ions, colourless ions. When they come together to produce this product, they end up being a red colour. So all of the starting solutions are a pale yellow colour. So we've left the reaction to reach equilibrium. So the equilibrium's lying somewhere in the middle. It's a pale yellow. When the chemicals are added, so when we add each of these chemicals in turn, if the colour turns red, then the equilibrium has shifted towards the product side. So it's going to make more and more of these, and it's going to turn red. Whereas if the colour turns more yellow, then that means the equilibrium has shifted towards the reactants. So these products are decomposing into the yellow iron 3 ions and the thiocyanate ions. So let's have a look at our results table and actually see what happens. So when we add FeCl3, so iron chloride, it's going to increase the reactant, and we can see that here. We have iron 3 plus ions in this equilibrium mixture. Now remember, all of this is in the one test tube, all of it. If we add iron chloride, we are adding iron 3 plus ions to the mixture, because as you know, iron chloride is a salt. If you have 3 chlorines to every 1 iron atom, then that means that the charge on your atom, on your ion, is going to be 3 plus. So you'll have iron 3 plus. If you increase the reactant, what actually happens in this mixture and that you would see in the experiment is the reaction turns from yellow, kind of pale yellow, to red. That means that the equilibrium is moving in this direction, so it's making more products. Let's look at another example. If we add potassium thiocyanate, we are again increasing the reactant. That's going to split up into a potassium ion and a thiocyanate ion, which has this negative charge here. Again, we are increasing one of the reactants. When we increase that reactant, the shift is also to the right-hand side. It's going to make more products, which is observed by the red colour forming in the test tube. So if we add any of the reactants, we are getting a shift to the right-hand side and more red colour produced. Let's see what happens when we remove a reactant. So remember, our ammonium chloride is going to remove these iron ions. So this time we are decreasing a reactant. So we're taking a reactant out. What's going to happen this time? This time it goes more yellow. So we can see a yellow colour forming in the test tube. That means that the equilibrium has shifted to the left or the reactant side this time. So the conclusion to this experiment is then, if you increase the concentration of reactants, that causes the system to make more products. So what it does is it just tries to undo the change that you have made. So if you try and increase the concentration of the reactants, the system will get rid of those extra reactants by turning them into products. And that will be a shift to the right-hand side, which is the product side. If you decrease the concentration of the reactants, that causes the system to make more reactants. Again, you have taken some reactants away. The system wants to replenish those that have been lost. So the equilibrium will shift to the left, which is the reactant side, to replace those lost reactants. So it just tries to counteract whichever change you make to it. The same goes with increasing product and decreasing products. If you increase the concentration of the product, it will try and get rid of those by making more reactants. If you decrease the concentration of the products, it will try to replace them by making more products. This is called Le Chatelier's principle. And it states that when a system is in equilibrium, the equilibrium position will move to counteract any changes that were made to the system. So it will try to reverse whatever you do to the system. Now, one of the trickier parts of this, it was quite easy in that example we just looked at to say, right, if we're adding salts, they're going to split up into their ions in solution. So we're adding this, that's adding a product. If we add this, that's adding a reactant. But what the questions will sometimes do is they will ask you about species which are added to the equilibrium mixture, which can decrease the concentration of reactants or products by reacting with them. So if you have acids or alkalis or hydrogen ions or hydroxide ions in your equilibrium equation and you add acids or alkalis, then that will change the system by reacting. For example, we have a question here. In the bleach cleaner, an equilibrium exists. So it gives you an equation here and says the label warns that the bleach cleaner should not be used with any other products as it may release chlorine gas. Explain clearly why mixing the bleach with an acid would shift the equilibrium to the right, resulting in the release of chlorine gas from the bleach cleaner. So some people at home like to do their cleaning with bleach, sometimes with vinegar. If in this scenario, this person was to mix the bleach with an acid like vinegar, you would get more chlorine gas release. That's what the question's asking. Why is this happening? Well, what we need to remember here is we need to remember what makes up an acid. For example, if we had ethanoic acid, for example, or any acid, we know that in solution, acids split up into hydrogen ions and whatever the other half of the acid is. If it was HCl, it would be hydrogen and chloride ions. You know your acids already. So if we have on the reactant side of our equilibrium hydrogen ions and we add an acid into this system, we are adding more hydrogen ions. So if we add more hydrogen ions, we are increasing the concentration of that reactant. and in doing so, we are pushing the equilibrium to the right-hand side. In adding hydrogen ions from an acid, the system will try and reverse that by removing them, and it will do that by making more products. Chlorine gas and water are the products. So by adding lots of hydrogen ions, the system reverses that by producing more products, and that is going to produce more chlorine gas. You need to explain that in quite a lot of detail to get the marks. So first of all, saying that adding an acid to the mixture will increase the number of hydrogen ions present. That in turn is going to increase the concentration of the reactants, and that shifts the equilibrium towards the products. Therefore, more Cl2 or chlorine gas will be released from the bleach cleaner. Make sure that you have that extra sentence in there as well about relating to the question. If you only have points 1 and 2 and don't actually explain what the question's asking, it's asking about the release of chlorine gas, so you need to get that in there to get the marks. Hopefully that makes sense. Let's try an example. So what I want you to do is I'll read through the example, and then if you pause the video, and then we'll go through the answer. I want you to try it yourself. So the addition of which of the following substances would move the equilibrium above to the right? So we have 4 substances here, and we want to know which one, if added to this equilibrium, will shift it towards the products. So pause the video now, have a think, choose an answer, and then we'll go over the answer. Okay, so we have an equilibrium here with chlorine gas and water, basically the opposite of the other question. And on the product side, we have hydrogen ions, these chlorate ions, and just chloride ions. The addition of which of the following substances would move the equilibrium to the right? So let's go through them. If we add hydrogen as a molecule is H2 gas. That's not going to interact or have any effect on anything in this solution. So we can just write off A. Hydrogen chloride, or HCl, if dissolved in water, is going to add some hydrogen ions into the mixture. Now remember, all of this equation is in the one mixture, in the one test tube if you like. So if we add hydrogen chloride, we're going to add both hydrogen ions and chloride ions. If we increase the concentration of the products, the equilibrium is going to shift to the reactant side and make more of those reactants. So that's not going to shift the equilibrium to the right, that would shift it to the left, so we're not looking for that one. Sodium chloride is a salt. If that's dissolved in water, it will split up into sodium and chloride ions. Chloride ions, again, are going to increase the concentration of the products, which in turn will move the equilibrium to the left to make more reactants. So it's not going to be C either. So the answer then from elimination, it has to be D, but I would like to explain why it is D. Because a lot of people will be looking at that and saying sodium hydroxide, how does that fit in here? There isn't any hydroxide ions. And those people would be absolutely right. It is the hydroxide ions which react with something in the equilibrium mixture. So if you have hydroxide ions and you also have hydrogen ions, then they will react with each other to produce water molecules. But what that does is the hydroxide ions pull the hydrogen ions out of that equilibrium to do that. So when you take hydrogen ions out of the equilibrium, then you are decreasing the concentration of the products. When you decrease the concentration of the products by pulling that out here, that will react with the hydroxide ion. You are then going to have to make more products to replace what has been lost. So by pulling the hydrogen ions out, by reacting with hydroxide, then the equilibrium is going to try and make more of those. So it will shift towards the product side or the right. That's why it has to be D. in that example. 3, we have already done this question. I just put it in earlier as a kind of little benchmark to make sure that we understood. So hopefully everybody knows the answer to this. Chemical reactions are in a state of dynamic equilibrium only when it's going to be D, the rate of the forward reaction equals the rate of the backward reaction. Example 4. The reaction that produces solid sodium hydrogen carbonate involves the following equilibrium. So again, we have our equilibrium equation. We'll always be given an equilibrium equation if we're asked questions about it. It says brine is a concentrated sodium chloride solution. Explain fully why using a concentrated sodium chloride solution encourages production of sodium hydrogen carbonate as a solid. So another explain fully question is going to require us to talk through exactly what's going to happen, how it's going to affect the equilibrium, and why. So if we add a concentrated sodium chloride solution, then that's going to obviously be dissolved in water. So it's going to contain both positive sodium ions and negative chlorine ions. The negative chlorine ions aren't really going to do much here. They're not really involved in this equilibrium. However, the addition of lots, because it's a concentrated solution, lots and lots and lots of sodium ions are going to increase the concentration of the reactants. So that's this side. So increasing the number of, or the concentration of the reactants is going to push the equilibrium to the right-hand side or the product side. That is going to make this product here, which is sodium hydrogen carbonate, as a solid. And those are the points that you need to answer that question. So first point, adding sodium chloride is going to introduce sodium ions and chloride ions. Adding more sodium ions is going to increase the concentration of the reactants. So the system's going to try and reverse this by getting rid of them and making them into products. So this moves the equilibrium position towards the products, making more solid sodium hydrogen carbonate. Now notice again in the question we're asked about sodium hydrogen carbonate as a solid, and I've mentioned that in my answer. So we wanted to, in this lesson, gain an understanding of what is meant by dynamic equilibrium and investigate how this is affected by different factors. Hopefully now everybody has a definition for dynamic equilibrium. That is a very, very popular multiple choice question. So if you know the definition off by heart, then you can immediately pick out the correct answer. Identify factors which can affect equilibrium. So that is concentration, pressure, and temperature. Hopefully we can explain why increasing or decreasing the concentration of reactants or products moves the equilibrium to the right or the left. In the next lesson, which is lesson 2, we will investigate what happens when we increase and decrease both pressure and temperature and what effect that has on the equilibrium position. If you have any questions about this lesson, then feel free to message your teacher on Google Classroom or give them a wee email.